chapters, okay, some review exercises. Okay? Let's start from RFID. So we'll be using the chapter 4 of the exercise. Okay? Let's start with exercise 3. Let's exercise number 3, chapter 4. Okay, topic is RFID. Okay, so this is actually taken from an example. Okay. And this exercise 3 says that a dynamic frame-Galois system is used to arbitrate 4 tags. So we need to solve collision out of 4 tags. Okay? And what we have to find is the average throughput. Okay, so the average number of tags that go through, that are arbitrated, after the first 2 frames of dynamic frame-Galois, knowing that the length of the 2 frames are R1 equal to 2 equal to R2. Okay? Okay, so let's say review some of the concepts. This is dynamic frame-Galois. Dynamic frame-Galois. Okay, how does this dynamic frame-Galois work? How does it work? We saw it yesterday, right? So it should be fresh in your mind. How does it work, this frame-Galois? Dynamic frame-Galois. So time is slotted first of all, okay, and then is framed more than slotted, which means that you have frame 1, okay, which is composed of some slots. Then you have another frame 2, which is composed of another number of slots, okay, and so on and so forth. So you have consecutive frames going on and on, okay. The rule of dynamic frame-Galois is that all the tags, all the nodes, okay, which are still to be resolved at the very beginning of the frame, okay, they have to choose randomly one slot in the frame. Okay? So in our case, we have 4 tags, n equal to 4, which means that at the beginning here, these n equal to 4 tags, each one of them, they will choose randomly one of the slots of the first frame. Okay, maybe tag number 1 goes here, tag number 2 goes here, tag number 3 goes here again, collision, tag number 4 goes here. Okay, then the rule of the dynamic frame-Galois is all the tags that were collided, so all the tags that chose the same slot, for example in this case 2 and 3 out of 4, okay, they have to do it again in the next frame. So the next frame here, 1 and 4 went through, they were solved, okay, because they chose one slot, each one of those, okay. So at the beginning of the second frame, I have a new number of backlogged tags, so a new number of tags that is to be resolved, is 2, is composed of tag 2. Okay, these new tags play the same game. So in the next frame, they will have to choose randomly one of the slots, and this goes on and on until they're all resolved. Okay? Clear? Very well. So in our case, we have the following setting. Our setting is the following. The first frame is 2 slots long. Okay? So this is our first frame. That's frame 1. Okay, and also the second frame is 2 slots long. Okay, that's frame 2. At the beginning of the, let's say, operation of this small network, we have n equal to 4 tags here. Okay, and the question is, if I set myself at the end of the second frame, so if I set myself here, what's the average number of tags that were resolved. So what's the throughput? Okay, in other words, we will have to find the expected value of what we call throughput, okay, after the second frame, at the very end of the second frame. Okay? How do we do it? We can do it sequentially. Okay? In other words, we can set ourselves here, okay, and ask ourselves what's the throughput at the end of the first frame. So what's the probability that at the end of the first frame a given number of tags was resolved or not? Okay, so let's do it. So let's focus ourselves on the end of the first frame. Okay? At the very beginning of the first frame, I have these 4 tags, that's frame 1. Okay? Frame 1. I have these 4 tags, and equal to 4 and 2 slots. Okay? That's frame 1. So we sit ourselves here at the end of the first frame. Okay? And we ask ourselves, what's the average throughput there, or better? What's the probability that during the first frame, a given number of tags were resolved using Fremalone? Okay? Using Fremalone means these 4 tags, they randomly choose one of the 2 slots of the frame, and depending on the choice, some of them may go through, or some of them may collide. Okay? Clear? Very well. So, how many tags can I possibly solve at the end of the first frame? Just one, right? I have 4 tags, 2 slots. Okay? So either they all collide, okay, or just one goes through and the other 3 collide. That's the only possible events at the end of the first frame. Okay? So let's give weights to these events. So let's find what is the probability that at the end of the first frame, the throughput, S1 stands for throughput at the end of the first frame, okay? The throughput is equal to 0, so they all collide, okay? And let's find dually what is the probability that at the end of the first frame, okay, I have one tag going through. That's the only 2 possible events, okay, at the end of the first frame. Either I solve 0 tags or I solve 1. It's impossible to solve 2 or 3 or 4 tags. That's obvious, right? Okay, so let's start from S1 equal to 1. What's the probability that out of 4 tags, only one chooses one slot and the other 3 choose the other slot? Right? That's the only way that one tag can go through. One tag choosing one slot and the other 3 choosing the other one. Okay? So the probability for a tag, any generic tag, to choose one slot is 1/2. Right? Okay? The probability for all the other 3 tags to choose the other slots is what? It's 1 minus 1/2 to the power of 3. Okay? I have 4 possible tags that can go through. Okay? And each one of these 4 can choose one of the 2 slots to go through. Right? That's the probability that one tag out of 4 is resolved after the first frame. Meaning, it's probability that one tag out of 4 generically chooses one slot, either this one or this one. Okay, and the other 3 tags choose the other slot.
Excuse me, can you repeat the just the probability before after 1 minus 1/2.
Okay, so up to here it's clear, right?
Yeah.
That's the probability that one specific tag, say tag A, tag 1, okay, chooses one specific slot, say this one here. That's tag A, okay. And the other tags, that is B, C, and D, they choose the other slot. Okay? This is exactly that probability. Okay? Then, in order for tag A to go through, okay, it can be this way or the other way around. So tag A can choose the other slot. Okay, that's why I have to multiply it by 2. Okay, then since I'm interested in any tag going through, okay, I have to multiply this probability here by 4 because it can be any of the 4 tags going through. It can be tag B, or tag C, or tag D, and so on and so forth. Okay, so I have to do it here by 4. Okay? Clear? And this is 1/2. Probability that 0 tag goes through is 1 minus. Right? It's the only 2 possible events. Okay, it's probabilities, so this here is 1 minus probability S1 equal to 1. Okay? Just to practice, let's find this probability without doing 1 minus. So let's sum up all the possible ways that no tag can go through. And let's find the probability directly without doing 1 minus. You tell me. What should I write here? Probability that no tags go through. Okay? In how many ways no tag can go through? Huh? In how many ways?
2 for each one of the slots every time the 4 tags choose the same slot. Plus
Okay.
the possibility that they sort each other 2 in one slot and 2 in the
Perfect.
other.
So at the end of this frame, I have 0 tags sort if they all choose the same slot, so they all go here, or they all go here. Okay, so that's one way. Or I have 0 tag going through if they split 2 in 2. Okay, so 2 tags go here, and 2 tags go here. In any case, I have 0 successful transmission at the end of the frame. So let's just write down the probabilities of these 4 events. Okay, the probability that all the tags choose the same slot, how much? What is it? Probability that all the tags, the 4 tags, they all choose one specific slot. Say this slot here.
1/2 to the power of 4.
Okay, so it's 1/2 to the power of 4. Okay, the probability that the same happens in the other slot is the same, right? So I can just multiply it by 2. That's the probability that the tag collide in that way. So they all choose the same thing. Okay? What's the probability that they collide in the other way? What's the probability of this event happening? Tag A, tag C go here, and then tag B and tag D go here. What's the probability of that event?
1/2 to the power of 2 and 1 minus 1/2 to the power of 2.
Okay, so the probability of this very event is 1/2 to the power of 4. So each tag need to choose one specific slot. Okay, it's 4 tags. Okay, so they need to choose one specific slot, A, C, B, and D, like this. Okay, so this is the probability of that specific event. Now, what I have to do is to count up in how many ways this can happen. So it can be A, C, B, D, A, B, C, D, all the possible split in 2 by 2. Okay? Clear? Clear? So all the possible split of 2 elements out of a set of 4 has a name that is 4 on 2. Okay? 4 over 2. Are you familiar with this writing? Yes? Okay, so this writing means 4 factorial over 2 factorial, 2 factorial. Okay, all the possible ways that you can take a set of 4 elements and split it in a subset of 2. Okay, which in our case is all the possible ways that 2 tags can actually collide in one single instance. Okay, so if we did it right, this is 1. There is 1 minus VS. Okay. Here. Okay, so let's get back to our original problem. Can I hear everything? Yes. So now we know that after the first frame, with probability 1/2, we solve nothing, and probability of 1/2, we solve 1 tag. Okay, so we have 2 cases here, right? So at the beginning of frame 2, either we have solved 0 tags, okay, or we have solved 1 tag. Remember that we want to count up how many tags we have solved at the end of the 2 frames. Okay? So we have 2 different, kind of bifurcation here, right? So either we have solved 0 tags or 1 tag. Okay? So if you want to picture it on a graph, it means that at the very beginning we are in a given point here. Okay? That's our the starting point of the first frame. Then at the end of the first frame, we travel to another point here, okay, with probability 1/2, and this path, this path happens with probability 1/2, okay. At the beginning we have 4 tags to be resolved. With probability 1/2, we still have 4 tags to be resolved, and it's always equal to 4, okay. Or we can take another path at the beginning, after the first frame, whose weight is still 1/2, okay, that lead us to a point where we have solved 1 tag. So we go down to 3 tags remaining. Okay? And this, whether I take this path or this path, it depends on the randomness for the process, right? Randomness that is measured by 1/2 and 1. Okay? Okay, very well. So, let's do frame 2. Frame 2. Okay, so we are at the beginning of the second frame. Okay, and here we have 2 cases, right? So either we are here, so either at the end of the first frame we travel to this path, so we still have 4 tags to be resolved. Okay, or we are lucky and we're here. That is, we solved 1 tag in the previous step, let's say. Okay, so if we are here, okay, so if n is still equal to 4, okay, then we have to solve the same problem as before, right? So if n is equal to 4, it means that we have a second frame whose size is 2, which is exactly the same as before, right? I have my 2 slots in my frame. I have 4 tags in this second frame. At the beginning of this second frame, I have to find what is the probability that at the end of the second frame I solved 1 or 0 tags. It's the same as before. Okay? So if n is equal to 4, the probability that at the end of the second frame I solved 0 tags is 1/2. Probability that at the end of the second frame I solved 1 tag, the probability is still 1/2. Okay? You agree? Same setting as before. Same number of tags, same frame size. Okay? If n is equal to 3, so if we travel this path after the first frame, okay, there's a difference there, right? Because we still have a second frame composed of 2 slots, but we have 3 tags that are competing for these 2 slots, right? Again, how many tags can I possibly solve if the setting is this one at the end of the second frame? 2 slots, 3 frames. Again, 0 or 1, right? It's impossible that I solve 2. Sorry, it's impossible that I solve 3 because I don't have slots enough. It's impossible that I solve 2 because there are 3 tags. So either say 0 or 1 tag. Okay, again, what's the probability that after the first, after this second frame under this setting, we have solved 0 tags? In how many possible ways they can collide such that at the end of the second frame nothing is solved? In just one possible way, right? So they all, the 3 tags, they all need to choose the same slot. Okay? What is probability is 1/2 to the power of 3, all the tags choose one slot, okay? Times 2, because I have 2 slots. Here. And then by difference, PS2 equal to 1 is 1 minus this thing here, that is 3/4, right? It's 1 minus probability that S2 is equal to 0. Clear? Fine, we're done in the sense that we can just, if it helps, we can portray the situation as like this. Okay, we have the 2 paths after the first frame. Okay, these 2 paths have weights which are 1/2. That's it, graphed there. Okay, here we have still 3 tags to be resolved. Here we have still 4 tags to be resolved. Okay, and then after the second frame, it may happen that if I'm here, okay, I solve either 0 tags or 1 tag. So I still have 2 paths more, okay, that lead me to ending point where n is still equal to 4. So I solve nothing after 2 frames. Okay. Or n is equal to 3 because I solve 1 tag. Okay? Clear? And then if I'm here, so if I'm in this case here, okay, again, I have 2 paths going down. The first one weights 1/4, okay, and leads to a case where I end up in n equal to 3 because I solved 0 tags after the second frame, okay. And the other one that weights 3/4, okay, that ends up in n equal to 2. So I still need to solve 2 tags. Okay. Clear? It's 1 minus PS2 equal to 0. Very well. So what's the throughput? The throughput, I have to weight by their probabilities all the possible outcomes. Right? So let's do it here. The throughput S is equal to 1. Okay. So if I do this path, if I go here and here, that's 1/2, and that's 1. Okay. So if I do this path, I end up in solving nothing. Okay. So the throughput should be, throughput is 0 in that case. 0 multiplied by 1/2 times 1. Okay? If I do this path, if I go here and here, I solve 1 tag, right? Because the backlog is 3. And this happens with probability 1/2 times 1/2. So I solve 1 tag after 2 frames with probability 1/2 times 1/2. It's this path here. Okay? If I end up here, I still solve 1 tag, because in the end I have 3 remaining, right? And this happens though probability 1/2 times 1/4, right? So it's 1 throughput weighted by the probability that is 1/2 times 1/4. Okay? And then in the best case possible, I take this path here, and I end up solving 2 tags, right? Which happens with probability 1/2 times 3/4. Okay, so it's 2 times 1/2 times 3/4. Okay, if you do math, the math should come out, I don't know, 9/8. 9/8. That's the average truth. So on average, in this setting, after 2 frames only, I show slightly more than 1 tag. Clear? Questions? No questions? Okay. Let's try to do number 9. Number 9, always about arithmetic. So we have always the dynamic prima law. Dynamic prima law system that is used to arbitrate 3 times. So n is equal to 3. What we have to find right now is the average duration of the arbitration time, knowing that the initial frame size is R1 equal to 3. Okay? Then the text says that we have to assume that the frame size of the following frames, or the consecutive frames, is optimally set to the exact value of the current backlog. Okay, so this thing means the following. As I told you before, right? Dynamic prima law, you have consecutive frames, okay, composed of slots. Okay. What we have to find in this exercise is the total duration of the arbitration process. So how many slots across all the frames, okay, frame 1, frame 2, frame 3, frame 4, do we need to arbitrate the 3 tags, okay, to be able to solve all the 3 tags. So we are not limited in this exercise to the first 2 frames, just like before. We just keep it running until all the 3 tags are solved. And what we have to find is this duration. So how, on average, how many slots do we need to arbitrate these 3 tags? Okay. The hint of the text is that after each frame, so at this point here, at this point here, at this point here, and this point here, okay, the following frame size, so the size of the following frame, is optimally set, okay, to the current backlog. This means that if here I still need to solve if at this point, after the first frame, I still need to solve 2 tags, so I solved 1 here, okay, then the size of R2 would be equal to 2, okay? If at the end of the second frame I still need to solve 2 tags, then R3 is equal to 2. Okay, so the frame size is optimally set equal to the current backlog. Current backlog means the total number of tags that still need to be resolved. Okay? Questions? How do we do it? So, we have to apply the recursive formula that we studied yesterday. Okay? And if you remember, this recursive formula was something like the total time, or better, the total number of slots that I need to spend to solve n tags, L of n, okay, it's equal to the frame size, the first frame size, which I have to pay anyways, right, the initial frame size, okay, plus all the possible combination of what can happen after the first frame. Okay, and the right thing is the following. The sum with e that goes from 0 to 2, okay, of L of n minus I, e I, probability that I've solved I tags after the previous frame. Okay, so that's the recursion that we have to solve. Okay? As I was telling yesterday, this sum is basically the total probability theorem. So after the first frame, given that I solved 1 tag, how many slots do I need to solve the remaining ones? Or given that I solved 0 tags after the first frame, how many slots do I need to solve those number of tags? Okay? So it's an application of the total probability theorem. I just weight all the possible events after the first frame, okay? And I do the recursion on these weights, on these probabilities. Okay? Clear? So in our case, this recursion is rather limited because this sum goes between 0 and 2 only. Okay? So we can just put numbers and names into this sum. R1 is equal to 3. Okay? Then I have to sum up L of 3. This is 3, right? Because n is equal to 3. Okay? L of 3 weighted by the probability that S is equal to 0. So I solve 0 tags after the first frame. Okay? Plus L of 2, probability that I've solved 1 tag after the first frame. Okay? Plus L of 1, probability that I've solved 2 tags after the first frame. And that's it. That's the recursion. Right? Is it clear? Okay. Can we, now the thing that we have to find is basically these probabilities, just like before. Right? So the probability that after that frame we solve 0 tags, 1 tag, 2 tags, 3 tags, and so on. Okay, why? Because then we have to put those probabilities into here to actually the recursion, to be able to calculate L of 3. That's what we need to calculate. Okay? So can we say something without doing any calculation of these probabilities? Remember that we are in the case where we have a frame of 3 slots, that is R1, the first frame, okay? And so R1 equal to 3 and n is equal to 3. So 3 tags choosing these 3 slots. Okay? Can we say something on PS1, PS0, PS2 a priori without doing anything, without doing any calculation?
PS2 is 0.
This one is 0. PS2 is equal to 0. It's impossible that after this frame, under this context, only 2 of them go through. Okay? Either no one goes through, or only one goes through, or all of them go through. Okay, that's the only possible events. So this one here is 0. Okay, I can just let's find the other 2. So PS 0 and PS 1. Okay, let's find PS 0. Let me find it here. PS equal 0. Probability that in setting 3 tags, 3 slots, 1, 2, 3, and 3 slots, no one of them goes, nothing goes. What is it? They all need to choose the same slot, basically. Okay, so it's 1/3 to the power of 3, 3 of them, multiplied by 3 slots. You agree? Okay, that's PS0. What do we need to find? Let's find PS1. PS equal to 1. Probability that only one of the 3 goes through. How much is it? How much is it? Okay, it must happen that one tag chooses one of the 3 slots, okay, and the other 2, okay, they choose the same slot. Okay, so it can be BC here or BC here. Okay. So this thing can be written as follows: probability of choosing, of one configuration, one choice out of the 3 is always 1/3 to the power of 3. That's all. Okay, then we have to count up all the possible ways that this can happen. Okay, so the first thing I shall count up is, let's say, how many groups of 2, okay, I can create out of a group of 3 tags. Okay, so how many ways I have to put together 2 tags out of 3. Okay, in how many ways I can put together the 2 tags that collide. It can be AD, BC, AD, CD. Okay, formally this is exactly as before, 3/2. Okay, clear? 3 ways. Then, once I have done the splitting, okay, in how many ways I can allocate the splitting to the 3 slots? Okay, so the tag that is going through can be any of the, how can I say, any of 3, right? Okay, and then once I have decided out of the splitting, okay, how to allocate, in which slot to allocate the tag going through, okay, I still have 2 other possibilities to allocate the group of 2. Okay, so it's 3 times 2. Should be, it's,
We didn't consider choosing 1 out of 3.
what do you mean out 1 out of 3?
First, we want to one of them be solved, so we have to choose at 1 out of 3.
It's the same. You can consider 3/1. It must be the same. And it should be 6/9, right? 2/3. PS equal to 3 is the difference between these 2. Okay, but let's do it directly. What is PS equal to 3? PS equal to 3 means that I have to allocate the 3 tags, okay, to 3 different slots. Okay, so the question is, in how many different ways, okay, I can order the 3 slots, sorry, the 3 tags, okay, assigning each one of them to one specific slot. This is 1/3, okay, multiplied by 3, multiplied by 2, or 3 factorial. It's the number of disposition of 3 elements, number of disposition of 3 elements, 3 factorial. Okay, and it should be equal to 9. Clear? Okay, so now we have numbers that we can use into this expression, right? So let's rewrite this expression using those numbers, okay? So this expression is something like L of 3 is equal to 3 R of 1 plus L3 weighted by PS0, that is 1, 9, right? So L of 3 multiplied by 1, 9, okay? Plus L of 2 weighted by PS equal to 1, that is 2/3. That's our recursion after, putting numbers in it. Okay? But now that we want to find L of 3, right? That's what we want to find. Okay? Still, we have this unknown. L of 2 is unknown. Okay? Here, L of 2 is the number of slots that we need to find, given that our backlog is 2. Okay? And here we can exploit the hint, the suggestion given by the text. The text says, after each frame, the frame size is set to the current backlog. Okay? So if after the first frame we end up in having solved one tag, so we have 2 remaining, okay, L of 2, then the next frame must be 2 slots long, okay, equal to current backlog. Okay, so to find L of 2, we have to be recurrent, right? So we have to imagine to be in this setting here, second frame, where the backlog is equal to 2, L of 2, okay? And we ask ourselves, what's the solution time at this point on, from this point on, right? So what is L of 2? Okay? L of 2 can be written just like we wrote L of 3. Okay? So L of 2 is equal to R of 2, R sub 2, number of slots in the second frame, okay, plus the recursion. Okay? So plus sum between 0 and 1 in this case, okay, of L of 2 minus I times probability of having solved I tags in the second frame in this case. Okay, so we just use the same expression, okay, starting at the second frame. Okay? By assumption of the text, we know that R of 2 is optimally set, so it's set to the current backlog, so 2 slots. Okay? So we have to find basically how much, what is the value of L of 2 using this recursion. Okay? So let's rewrite it in a more compact way. This is L of 2 equal to 2 plus L of 2 probability S equal to 0, okay, plus L of 1 probability S equal to 1. Okay. Careful that this S is a throughput after the second frame. So in this set, 2 slots, 2 stacks. Okay? So it's 2 plus L of 2, okay, multiplied by the probability that no tags are solved. How much is it? Probability that 2 tags, 2 slots, no one goes to. It's 1/2. Okay, 1/2 to the power of 2 times 2. So it's 1/2. Right? Plus L of 1 times probability that 1 tag goes to. That is 0. Right? That's 0. It's impossible that 1 tag only goes to. Either they all collide or they all go. Okay? So that's the formula that we can use to find L of 2. So we know that L of 2 is equal to 2 plus L of 2, 1/2. Okay? If we solve this in L of 2, it should come out that L of 2 is equal to 4. Okay? So at this beginning of the second frame, it takes still takes 4 slots to solve the 2 tags on average, actually. Okay, and we are done. Because we can take this value here, L3 equal to 4, we can put it in here, okay, write it down that L3 is equal to 3 plus L3 times 1/9 plus L2, that is 4, okay, times 2/3. Okay?
How do we know that we are left with 2 tags after the first one?
How do we know?
That we are left with 2 tags after the first one?
Uh,
The probability is the biggest one of solving 1 tag?
So the question is why?
Why 2 slots? Why 2 tags after the first slot?
Because you condition yourself of being 2. So with probability 2/3. Okay, after the first frame, you have solved 1 tag. Right? So you still have 2 to be solved. Okay, so under this assumption that you have solved 1 tag in the first frame, which happens with probability 2/3, okay, you end up with a second frame of 2 tags results. Okay? And we are done because this is an expression in one single variable, which is L3. Okay, that is exactly what we want to find. And if you do the math, you should find that L3 is something like 51 over 8. Okay? So more than 10 slots, more than 5 slots to solve the initial 3 tags. Here, okay, so to generalize, in all these cases, you start with the initial recursion, so you start with this formula here, okay. What you have to find is the first probabilities, so the probabilities to solve 1, 0, 2, 3, 4, n tags after the first frame, okay. And then to do the recursion. So you condition yourself of having solved 1, 2, 3, 4 tags after the first frame, and you find L of 2 in this case. So L of n minus 1 in the more general case. Okay? And you keep doing this recursion until you find a closed form expression of what you are finding. Okay? If you do so, you recurse back. You go back to the original formula and substitute back the value of the last L variable that you have calculated, in this case L of 2, okay, and you close the recursion. You find L of 3 in this case. Okay?
To decrease the number of tags from 3 to 2 after the first frame, yes?
Yes.
So there is a probability that none of the tags will be solved. For example, PS0 is 1 out of 9.
Yes.
So why we didn't consider that starting the second frame with
Here.
3 tags?
So if 0 tags are solved after the first frame, okay,
Oh, it's
you get to a point where you still have 3 tags, so the next frame is 3 slots down. Okay, so it's here. So you go back to the previous one. Okay, but you have lost the first 3 slots of the first frame. Okay, here. Is it clear?
yes.
So it's the same as the graph that I showed you before, right? So if you want to see it graphically, okay, it's like a 3. Okay, so that's the first point. Then after the first frame, in our case, we just had 2 possible outcomes, right? Okay, so n was equal to 3. Okay, and we only have 2 possible outcomes there. So n is still equal to 3 or n equal to 2. Okay, so you ask yourself, if I'm here, which happens with probability 1/9, okay, how much time does it take to solve the thing from here on? Okay, you have the same 3, right? Because from here you still have 2 branches, n equal to 3 or n equal to 2. Okay, and you go on like this. Okay, once we got here, we know that L of 2 is equal to 4. Okay, so if we go this way, we know what is the average time to solve the old tax. Okay? If not, so you can just explore the tree in a compact way to the recursion, okay? In this way here. Okay? Let's change a bit topic now. Let's do one on 15.4. So chapter 2. Okay. And let's do exercise 8. That's exercise 8 on chapter 2, 15.4. Or GB. Okay, so we're given a personal area network with a pump coordinator. And the 3 modes. Mode 1, mode 2, mode 3. Okay. Each mode is assigned a slot of 1 millisecond. So the slot duration T of S is equal to 1 millisecond. And the guaranteed, each slot in the guaranteed time slot part can carry 1 single pair. Okay? Then the beacon interval is 210 milliseconds. Okay. And the cap, the collision axis part, let me write it here. The number of slots in the collision axis part is equal to 7. And then each one of these 3 tags has 1 slot in the collision free part. So the number of slots in the collision free part is equal to 3. Okay? Then, the 3 modes, they have the following traffic pattern. So mode 1 generates uplink traffic to the pump coordinator according to a Poisson point process with parameter lambda 1. Lambda 1, that is 1 packet per second. Lambda 2, mode 2 generates traffic in the uplink according to Poisson point process with lambda 2 equal to 0.01 packet per second. Okay. And lambda 3 is the same, but lambda 3, so it's all Poisson point traffic, but it's 0.1 packets per second. Okay? Then, we also know that the 3 modes and the pump coordinator, they have similar hardware with the following energy consumption per unit slot. Okay, that is, in each unit slot, the energy for sleeping is 5 microjoule. The energy for being idle, it's 4 millijoule. The energy for receiving is 6 millijoule. And the energy for transmitting is 7 millijoule. Okay? What we have to find is the average energy, energy or average power consumed by the 3 modes. Okay, in this setting. Okay? Okay, so let's see what's the context. The context is the following. It's 50.4, beacon enabled, collision free part, collision access part. So we have a beacon interval whose size is 210 milliseconds that is composed as follows. As usual, we have the beacon slot, that's the first slot, right? Then we have 3 slots in the collision free part, and CFP is equal to 3 slots in the collision free part, okay? That are assigned to mode 1, mode 2, and mode 3. 1 slot for the 3 modes, okay? And that's the collision free part. And then for some reason we also have in this case a collision access part, okay? That is composed of 7 slots. So 1, 2, 3, 4, 5, 6, 7. Okay? That's our collision access part. Okay? And then we have the whatever number of slots we have in the sleep part. So where they all go to sleep. All the 3 modes, they use only their own slot in the collision free part to send up traffic to the pan coordinator, and the traffic they have is not deterministic, but is given by these statistical parameters. Probability given by a Poisson distribution. Okay? What we have to find is the average energy consumption of the 3 modes. So E1, E2, and E3. Okay, so as usual, as always, the amount of energy consumed by a mode depends on depends on what the mode does during the beacon interval, right? So depending whether it is transmitting, receiving, or doing nothing, or sleeping, then it will amount. We will have to sum up for that mode the amount of consumed energy. Okay. So in the beacon slot, all the 3 modes they are receiving, right? So that's a deterministic contribution on energy consumption for the 3 modes. Okay. In the collision access part, they are doing nothing. Okay, so they're idle in these 7 slots, and in this part here, they're all sleeping. Okay. So for all the 3 modes, beacon slot, collision access part, and sleep, they are deterministic sources of energy consumption. Okay? What changes is what happens in the collision free part. Okay? Because in the collision free part, one mode might have or might not have a packet to send to the pan coordinator in that beacon interval. Okay? And depending whether the mode has or does not have any packet to be sent to the pan coordinator, it might consume more or less. Right? So let's find first what is the probability that a given mode has at least one packet to be sent to the pan coordinator. Okay? To find this probability, that we call PI, probability that each mode of type I, 1, 2, 3, okay, has a packet, at least one packet to be sent to the pan coordinator, we have to use this information here, right? So we know that packets are generated according to Poisson point process, okay? Which means that the probability that the mode has no packet or better generates no packet in one beacon interval, okay, is given by e to the power of lambda I times pi, right? This is under Poisson the probability that the mode of type I has no packets, or better, generates no packets, 0 packets in one beacon interval. Okay? The probability that one mode has at least one packet in one beacon interval is simply given by 1 minus e to the power of minus lambda times pi. Okay? So that's the probability that mode of type I has at least one packet to be sent in its own slot. Okay? So it's the probability that the mode of type I actually uses its own slot for transmitting information. Okay? Clear? we are done, okay? Because we can safely write down the energy consumed by the motor type I, so the generic motor type I in this case, right? To write it down, let's suppose, since the text does not say anything about it, okay, let's suppose that all the three modes, they are not in range. The transmission of one mode is not overheard by the other two. Okay, so they're not in range. So if the text says nothing, you can safely assume that they're not in range. Okay? So if they're not in range, the energy consumption of the generic mode is given by the following. Beacon slot is receiving, right? Okay? Then, in the collision-free part, with probability pi, the mode is transmitting something, okay, in its own slot. With probability 1 minus pi is idle in its own slot, so it's doing nothing in its own slot, it has nothing to transmit, okay? And since they are not on in range, in the other two slots belonging to the other two guys, okay, the mode is idle, so it's doing nothing. Okay? And what I wrote so far is the energy consumed up to this point, so at the beginning of the collision axis part. Okay? Then I have to sum up the energy consumed in the collision axis part, that is 7 times E idle. Okay? In the 7 slots of this collision axis part are doing nothing, so they are idle. And then I have to sum up the energy consumed while sleeping. That is E sleep times, let me call it N sleep, so the number of slots in the sleeping part. You agree?
This probability isn't a normalized probability.
What do you mean by normalized?
The summation or over probability should be 1.
Yes, it's like that.
It isn't a normalized one. Because when we sum up between one loss, it isn't what we want. It should be divided by the summation or all of the probabilities to be normalized.
So, this is the sum of different probabilities. It's a probability, right? So it's a probability that, let me call it like this. It's a probability that the number of packets of node I, okay, generated in one Beacon interval, okay, is higher or equal than 1.
Yes, it's true. It should be normalized, yeah?
Define normalized. It's a probability, so it's by default normalized. It's by default normalized. Huh?
I think it should be divided by summation over all E minus lambda IPI.
You want to divide this by what? It's a probability. So it's a number between 0 and 1. Okay? And if you sum it, this thing here, okay, with the probability of plus E minus lambda I, this sum up to 1.
Yes. Yeah. But, so for one of them, for one of the probabilities, we should divide each divided by the whole summation all over the probabilities.
Let's discuss how. Anything else on this one? Okay, so let's now assume that they are in range. Okay, so let's do the same calculation, assuming that they are all in range. So the 3 modes can overhear, can actually receive the transmission of the other 2. Okay, how does it change? So that's the case of no, let's say not in range, not in range. Okay, let's do the case where they're in range. Okay, and let's do it for 1. The energy consumed by mode of type 1, if they're in range, it's E on X for receiving the beacon, right? Then, just like here, in its own slot, it can transmit or not. Sorry, it might have a packet to be sent or not. Okay, so it's exactly like that expression there. So P1 ETX plus 1 minus P1 E idle. That's for its own slot. Okay. Plus, in the slot of mode of type 2, say, okay, if mode of type 2 is transmitting, which happens with probability P2, right? This guy is overhearing, so it's receiving something, let's say, the physical layer. Okay. Or if P2 is not transmitting, 1 minus P2, okay, then our mode of type 1 is higher. Okay, plus the same thing for mode of type 3. So if mode of type 3 is transmitting, I'm receiving. If mode of type 3 is not transmitting, so 1 minus P3, okay, then I'm idle. Okay, then I have the collision access part, so 7 the idle. And then I have the sleep part. So n sleep times okay, so that's the case where the case in range. Questions? So in all these exercises, suggestion is, let's say, think and reason slot per slot. So ask yourself what's the energy consumed by one node in one slot, and do it slot per slot in all the slots of the collision part, the collision access part, the sleep part, the interval, and so on. Okay. Watch out on the probabilities. So the energy consumed in one slot may depend on what the node does in that slot. Okay, and these in turn might depend on some probability. Okay, so first find the probability that a mode is actually using one slot for transmitting, receiving pairs, and then do this sum, okay, slot per slot. If you do like this, the error probability is very low. Okay. Questions? Let's do another one. Which one? Let's do. That's number 22, same chapter. 22, So we are here in another network, that's the path coordinator. And then we have here 4 nodes. 1, 2, 3, 4. Okay. It's beacon enabled mode. Mode 1 and 2, they have statistical traffic towards the path coordinator with the following probability distribution. The probability that R1 is equal to 5 bits per second and is equal to 0.2. Probability that R1 is equal to 75 bits per second is equal to 0.6. Probability that R of 1 is equal to 0 is 0.6. Okay, so that's the characterization of the traffic of mode 1 and 2. So that's the same for mode 1 and 2. Okay, the rate, the probability that the rate mode 1 and 2 is 2 to 5, 75 or 0 is 20%, 60% or 20%. Okay? Then mode 3 and 4, these two modes here, they have the deterministic rate R3, 4 of 5 to 5 bits per second. Okay, 525 bits per second. Okay. Then in this case, the path coordinator has to deliver downlink traffic. So that's for the uplink. So it's from the nodes. That's the uplink from the nodes to the path coordinator. Okay. In this case, also the path coordinator has to send downlink traffic to the nodes. Okay. And this traffic, in turn, is characterized as follows. So the traffic directed to mode 1 and 2, okay, has this property. The rate, the probability that the rate from the path coordinator to 1 and 2, okay, is equal to 75 bits per second. It's equal to 0.5. The probability that the rate from the path coordinator to 1 and 2 is 2 to 5 bits per second is equal to 0.1. And the probability that the rate from the path coordinator to R1 and 2 is equal to 0 is 0.4. Okay, so also the path coordinator has something to send it down, okay, which is something new with respect to the previous cases. Then the rate from the path coordinator to modes 3 and 4 is deterministic and it's 300 bits per second. Okay, and this is the downlink. Okay, uplink left hand side, downlink right hand side. Okay. So, assuming that the active part of the beacon interval is composed of collision-free part only, so no collision axis part, the modes and the path coordinator use packets of B equal to 128 bits to send their information in the uplink and downlink. So that's the packet size. Okay. The nominal rate, which fits exactly one slot. The nominal rate is the usual 250 bits per second. Okay. What we have to find in the first place is the dimensioning of the beacon interval. So how long is the beacon interval? How many slots we have in the collision-free part, and the slot duration, and so on and so forth. So the same stuff as before. Okay. So the main difference here is that basically in the structure of the beacon interval, okay, we will have, let's say, in the collision-free part, okay, that's the collision-free part, CFP. That's the slots in the collision-free part. Okay. We will need to have in this collision-free part some slots which are dedicated to the uplink. Okay. This here. So slots that are dedicated to hosting traffic from the modes to the PAN coordinator. Okay. But we need also slots for the downlink in this case. Okay. So slots that the PAN coordinator can use to send traffic down. Okay. And then we always have the, let's say, sleep part. Okay, so the number of slots of the CFT collision-free part includes uplink and downlink. Okay? Very well. So, first thing we have to find is the beacon interval duration. Okay, as usual. Okay, and to do that we can just impose that the beacon interval duration is such that if we assign a slot to a mode of type 1 whose minimal rate is 75 bits per second, okay, then the duration of the beacon interval is compliant with that rate. Okay? So we want to impose that the minimal rate of mode of type 1, 75 bits per second, that's the minimal rate overall. Okay? We want to impose that this 75 bits per second, okay, is actually equal to what you can deliver if you use just one slot in the beacon interval. Okay, so small b over bi. Okay, if we assign one slot here to a mode of type 1, for example, in each beacon interval, okay, we want to impose that this slot per beacon interval is equivalent to a channel whose rate is 75 meters. That's the minimal rate. Okay? Okay. So, using this expression, we can find that the beacon interval should be equal to 1.7 seconds. Okay? So we know how long is this beacon interval. Okay? And the next thing we should find is the number of slots in the collision-free part. So how many slots do we need to have in the collision-free part? Okay? To find the number of slots in the collision-free part, we need to be compliant with the requirements in terms of the rate. Okay? So we shall assign to all the modes a number of slots which is enough, okay, to host their worst case in terms of the rate. Okay? So what's the worst case for a mode of type 1 or 2? The worst case is this one, right? When they need a channel of 2 to 5 bits per second, 225 bits per second. Okay?
I have a question. What if we have different rates, different lowest rates in downlink and uplink?
You choose the minimum.
It doesn't matter if you choose in uplink or downlink.
It doesn't matter. The question was, what if we have different lowest rates in the uplink and the downlink? Okay. To find the beacon interval, you always pick the minimum. Okay. Regardless if it's uplink or downlink. Okay. So the number of slots needed by mode of type 1, which is exactly the same as the number of slots needed by mode of type 2, because they have the same worst case, let's say. Okay. Is given by the ratio between their worst case rate, 2 to 5, okay, and the best case rate, okay, or the one that we use to dimension the beacon interval. Okay, that is 3 slots, right? So if one slot carry a channel whose rate is 75 bits per second, if I need to have a channel of 225 bits per second, I need 3 slots. Okay, 3 times more slots. Okay. Then we can do the same for N3 and N4. N3 and N4 they need a rate of 5 to 5, 525 bits per second. 525 are 3, 4 divided by 75 bits per second. 75 feet per second is equal to, should be 7, right? Correct? Yes, 7. Okay. I need to give to motor type 3 and 4 a number of slots which is enough to support 5 to 50%. So I need to give them 7 slots each. Okay? And then I have the same stuff for the pan coordinator. So we are set for the uplink package, right? We need to find the same assignment for the downlink package. So I need to assign to the pan coordinator a number of slots which is enough to support all those traffic, all that traffic. Okay? So the number of slots the pan coordinator needs to send down to mode 1, okay, is to 5. In the worst case, okay, so it needs 3 slots, which is exactly the same number of slots that it needs to send down to mode type 2, okay, because the requirements is the same, traffic requirements is the same, okay. M3 pan coordinator is equal to M4 pan coordinator, okay. That is 7550 should be 4 slots each. Okay. Clear?